Okay, so let's take a look at the following two scenarios and decide which of the two is a binomial setting. Let's say we shuffle a deck of cards. We turn we turn over the first 10 cards one at a time. We're defining y as our random variable to be the number of aces that you observe. So notice you're taking the cards out of first 10 cards out of the deck, you're turning them over one at a time. How's that different from the second scenario? You're shuffling the deck of cards, you're turning over the first card, putting it back in and shuffling it again. We're repeating this 10 times. We're going to let y equal the number of aces you observe. All right, so there's a difference between these two. With the first one, letter A, notice you're taking a card, pulling it out of the deck, leaving it on the table, looking at what it is. Taking a second card, pulling it out of the deck, leaving it on the table, saying what it is, so on and so forth. So that means each time that you're doing this, the first time you did it, there was 52 cards in the deck, so you had a 4 out of 52 chance of choosing an ace. The second time you do it, notice that since you already have that card sitting on your desk, you're not putting it back in, there's only 51 cards left in the deck. The second time you do it, there's only 50 cards left in the deck. So the probability of getting an ace is changing each time because that denominator started at 52, then it's going to 51, 50, so on and so forth, all the way down until 10 cards. Now the second one, notice that when you do this, you are putting the card back in the deck. So the probability of getting an ace each time is not changing at all, because even if I pull an ace out of a deck, I have 4 out of 52, I'm putting that card back into the deck, and then that means I still have 52 cards to choose from. I've replaced it back into the deck, therefore the probability is not changing. So letter B was our binomial setting. For the first one, each trial is not independent. If we turned an ace over the first time, then that means the second time my probability of getting an ace is not a 4 out of 52, it's a 3 out of 51. However, in part B, we're putting the card back in, so each trial is independent of each other. So this would be a binomial setting with n equals 10, choosing a card 10 times, and in this case, y is 4 out of 52, because the aces you observe, there's a probability of 4 out of 52 of getting them each time. All right, so let's just take a minute. We're going to start looking at some binomial probabilities. So remember, in many games where you roll a dice, a 6 is desirable. Think about trouble. To get out of home, you want to roll a 6. So the probability of rolling a 6 when you have a fair die is 1 out of 6. It gets confusing. Rolling a 6, 1 out of 6. Now, make sure we're defining what x is. It's our random variable. It's the number of 6s in 4 rolls of a fair die. So that tells us that x is binomial. All right, we've defined what it is, the number of 6s that we're getting. We have a fixed number of trials, n equals 4, and a probability of getting 6 is 1 out of 6. So what is the probability that x is equal to 0? What does that mean? That means what is the probability that we roll a dice 4 times and none of them are going to be 6s? So how can we figure this out? We know that the probability of rolling a 6 is equal to 1 out of 6. The probability of not rolling a 6 is the complement. All right, so we want to find the complement. So if we have a probability of rolling a 6 is 1 out of 6, the probability of not rolling a 6, there's 5 other choices, 1, 2, 3, 4, 5, is 5 out of 6. Okay, and we're going to raise that to the 4th power. Why? Because this is saying the first roll did not get a 6, second roll did not get a 6, third roll did not get a 6, fourth roll did not get a 6, or 5 out of 6, the probability raised to the 4th is 0.482. Okay, so that's basically telling us each time that we roll a dice 4 times, we're not rolling a 6. All right, now what happens if it gets a little bit more complicated? What's the probability that x is equal to 1? So that's saying what is the probability that we roll a die 4 times and get exactly 1 6? All right, so let's think about this. This is a little bit more complicated. There's a bunch of possible outcomes if we're going to roll a die 4 times. We can roll a die and get a 6 on the first, the second, the third, or the 4th roll. So the position of where we get that 6 accounts on our probability. So here we can get a 6 on the first one, 6 on the second one, 6 on the third one, 6 on the 4th one. So let's take a look at how we can get the probability. So 5 out of 6, that's the probability of not getting a 6, that's 3 times, times the probability of getting a 6 1 time, plus the same thing. So we have 5 out of 6 to the third, because 3 not 6s, and then 1 6 on the second roll, 1 6 on the third roll, 1 6 on the 4th roll. Okay, so how can we sort of simplify that? Well, notice how they all have the same probabilities. 5 out of 6 not rolling a 6 to the third, because there's 3 ways that I'm not rolling a 6, times 1 out of 6, because I'm going to get 1 6, this is when I'm getting a 6. The probability of getting a 6 is 1 out of 6. And there's 4 different ways that can happen because I can get a 6 on the first roll, the second roll, the third roll, or the fourth roll. Okay, so that makes the probabilities a little bit more complicated. So x equals 1 is saying I have 3 failures and 1 success each time. However, there are 4 ways this can happen. So instead of adding, which you could do, you can also just multiply that by 4. 3 failures, 1 success, 0.3858. Okay, that one wasn't too bad. Now, what happens if probability of x is equal to 2, x is equal to 3, x is equal to 4? So I have 2 6s, 3 6s, 4 6s. Well, this can get a little bit more complicated. If x is equal to 2, I can have successes on the first 2, first and third, first and last 2, middle 2, second and fourth. So if you notice, each of these have 2 successes where I have the 6s and 2 failures. All right, so 5 out of 6 is not getting a 6, 2 failures. 1 out of 6 is getting a 6, 2 successes, but then we're multiplying that by 6 because there are 6 possibilities where that can occur. Okay, that gets complicated. How about x is equal to 3? So I'm basically having 3 successes, okay, in each of the trials and 1 failure, okay, in each of the trials. But how many ways can that happen? Well, that can happen 4 different ways. Now, what about x is equal to 4? That one's not too bad because that means there's only one way that I can roll a die and get all 6s. I'm going to have 4 successes. So 1 out of 6 is the probability of getting a success raised to the 4th. Now, this can get complicated because every single time are you going to want to sit here and figure out the number of possibilities. This part's not too bad, saying there's going to be 2 successes, 1 out of 6 is the second, so that's the probability of getting a 6, times 2 failures, 5 out of 6, not getting a 6. It's this 6 out front that says, well, how do I figure out how many possibilities or how many ways can the successes occur when I roll the die? All right, the binomial probability or the binomial formula is going to help us get these coefficients of 6, 4, and 1 without actually writing out all the probabilities. Okay, so let's examine this formula and see if we can come up with a general formula for binomial probabilities so that we don't have to write out the probabilities every time. All right, so probability that x is equal to 2, that's telling us out of 4 rolls, we want exactly 2 6s, or out of 4 rolls, we want 2 successes, okay? We know that we have 4 trials. We know that we want to have 2 successes, so we're going to define k to be the number of successes that we want, and we know the probability of our success is 1 out of 6. All right, so the probability of x is equal to 2 was there were 6 different ways that we can get 2 successes. Probability of success is 1 out of 6 to the second. Probability of failure is 5 out of 6 to the second. Give us our answer. Now, notice this says the probability x is equal to k. So this is saying the probability that x is equal to the number of successes. In this case, it's 2. Now, if you remember this from our previous unit, this is our combination formula, NCK. Okay, so what does that mean? N is the number of trials that we have. Combination is saying, all right, remember the combination gives us all of the possibilities that this can occur, all right, with 2 successes. The P to the K is saying, what is the successes? 1 out of 6, and we want 2 of them, because remember K is our successes, we want 2 successes. 1 minus P is basically the complement, or the probability of the failure. So the probability of the failure is 5 out of 6. And then 1 minus k is basically like saying, we'll complement again, or how many failures do you want? In this case, we want 2 failures. So NCR is our combination. You can get that on your graphing calculator, where N is the number of trials, and K is the number of successes that you have. And that's under your probability portion on your graphing calculator, which is in the graphing calculator notes if you want to go through that just to make sure that you know how to get that from your graphing calculator. So if we have the probability that x is equal to k, it's the number of possibilities, the numbers of ways that I can get 2 successes, the probability of successes raised to how many successes I want, times the probability of failures raised to the number of failures we want. So this number of possibilities is just the combination of the number of trials and the number of successes that we want, and that will tell us how many possibilities that we have. All right, so let's try an example of this. In a binomial setting, remember we're always defining our random variable x, and is the number of successes, okay, and n is the number of independent trials. We're always interested in finding the probability distribution of x. Okay, so when you read a problem, just check and say, hey, can this be a binomial distribution? And if it can, that's going to help you. So each child of a particular pair of parents has a 0.25 probability of having type O blood. Genetics say that children receive genes from each of their parents independently. If these parents have 5 children, the count X, we're defining what X is, of children with type O blood is a binomial random variable with n is equal to 5 trials, there's 5 children, and the probability of success, or the probability of them having the type O blood, is 0.25. So in this setting, a child with type O blood is a success, and a child without the type O blood is a failure. What is the probability that X is equal to 2? So you want to understand what that means, what the probability that x is equal to 2 means. That means that out of 5 children, I want to have 2 of them that have type O blood and 3 of them that do not. So we're just going to write it out this way. 2 successes and 3 failures. So the probability of success was 0.25, the probability of failures was 0.75, 0.25 squared, so that's like your k, or sorry, your p raised to your k, which is the number of successes, your failures raised to how many failures you want, the probability of failures raised to how many failures you want, and your answer. But that doesn't necessarily, this isn't the final answer, because I'm not necessarily going to get the first 2 children that have type O blood and the last 3 that don't. How many ways can I get 2 children with type O blood and 3 children that don't have it out of 5 children? That's where we're going to use this combination formula. If you wanted to, you could write this out every single solitary time, all right? 1, 2, 3, 4, 5, 6, 7, 8. So in this case, we know that there's 8 ways that that can happen, all right? So the probability of each of these is the same as the first one that we figured out, 0.02637. Sorry, that was 10. I clearly couldn't count, but we'd have to multiply that probability by 10 because there's 10 different ways that that arrangement can occur. So can we use our combination formula to do this instead of writing out all 10 arrangements? Okay, absolutely. So remember, the probability of x is equal to k, that's saying in this case successes, the probability that we want exactly 2 successes in 5 children, okay, that would have been the number of arrangements, probability of success, probability of failures, or in our previous case, that would have been 5C2, okay? So 5C2 on your graphing calculator would have given you 10. So the number of ways of arranging k successes, so 2 successes, let's say among n observations or 5 observations, is given by the binomial coefficient. So hopefully you remember this from our probability unit or maybe from a previous math class, but we write this binomial coefficient as nk in this sort of set of parentheses, right? So n is the number of trials, 5 trials, k is the number of successes, 2 successes. That is equal to n factorial. So remember, n factorial is, so n factorial, if n is 4, that would be 4 times 3 times 2 times 1, divided by k factorial, in that case was 2, 2 times 1, and then n minus k, which is, in that previous case, 5 minus 2, so that would be 3 factorial, which is 3 times 2 times 1. All right, and that's basically what that formula says right here. Your graphing calculator will do this for you so you don't have to write this out every time. And understand that 0 factorial is basically 1, and the reason that it's 1 is because they're saying if I want 0 successes, there's only one way to do that. Okay, so our official binomial probability formula takes what we just talked about on the last 2 slides and puts them into one formula right here. All right, so the probability that x is equal to k, or x is equal to, let's say, 2 successes, is equal to the binomial coefficient, how many trials you have, and then how many successes you want, times the probability of success, how many successes you want. 1 minus p is the probability of failures, and then n minus k is the number of failures basically that you want. So k is your number of successes, p is our probability of success, this is the probability of failures. Now, like I said, on your graphing calculator, this nk, n, that's basically saying nck, your graphing calculator will give you that combination formula. All right, so what's on the AP Statistics formula sheet? This is the formula that will be on the formula sheet. Just make sure you need to show the first few numbers plugged into the formula